That sort of looks like the coefficient of thermal expansion again, except I have the wrong term there, don't I?
Isn't that weird?
VDT, no, that's right, the VDT at constant pressure. So that is right, so that's alpha again.
Well,
Or V alpha. Go back and find out. Yes, that is V times alpha. We've used it before. But I'm not going to do that just yet. Well, it's equal to that. That's true, but I'm not really wanting to go there. Assume a perfect gas. V is nRT over P. Take the derivative of that with respect to T at constant pressure. Well, nR over P can now come out, and I get dT. G. We've seen that before a couple times, haven't we? That's 1. So dV dt over P is equal to nR over P. So I come back to that equation, which I'm going to write on the top of the next page, and substitute. And for that derivative, I get nR over P. G. P cancels out. Now I'm going to substitute that back into this equation for the difference in the heat capacities. I'm going to substitute it right there. Okay. So I have that Cp minus Cv is equal to the partial of H with respect to T at constant pressure, which I've just shown is all of that, minus partial of U with respect to T at constant pressure. Okay. Minus du dt at constant pressure. That difference is the difference in the heat capacities, and I've substituted for this. But don't those cancel out? I've just rigorously proven that the difference in the heat capacities for a perfect gas are equal to nR. Or if we have molar heat capacities, the difference is R. I told you that when we did the gamma experiment. We used that piece of information to allow us to calculate Cp. We derived it, or I used it again a 3 days ago and said we would later prove it. We've now proven it. For a perfect gas, we've proven that to be true.
So R is the constant for heat capacity of the gas.
R is the perfect gas constant. But it turns out the difference in Cp and Cv for a perfect gas is equal to the perfect gas constant. And we use that approximation even for gases that were not behaving perfectly, because it's still a good place to start. Working anything out more correctly turns out to be pretty complicated. assume we do not have a perfect gas for a moment. Then what do we have to do?
The Van der Waals equation.
Well, we could stick a Van der Waals equation in there and do that. But we could go a little bit better. If you come back